So now that we have completed the challenge of, of elimination reactions, we move on to our third foundational reaction, which is the addition reaction. It is more straightforward, and along with it, we're going to also explore two new ideas, synthesis and complex mechanisms, both of which we will explore more in depth next semester. But for now, just to note, synthesis is the process of creating a plan, a set of reactions in order to start with a simple molecule and make a more complicated one. This is actually taken from an article about the art and science of synthesis as it related to Breaking Bad, and so I link this on our page for this class today, and it's kind of a neat article. And it points out that methamphetamine, which only takes 2 synthetic steps, actually really isn't a very interesting synthetic problem. And Walter White pointed that out, if you've ever seen the Breaking Bad show or television show. And in fact, there's a lot more, really much more interesting and engaging synthetic problems. And so you can make, for instance, a molecule, palytoxin, 140 different synthetic steps, over 64 stereocenters, lots going on there, lots of steps to prepare that. Paclitaxel or Taxol, it's also called the anti-cancer drug, 51 steps to prepare that, 11 stereocenters. And there's always more synthetic problems to solve, how to actually make these problems, and how to visualize doing so. And so this idea that it's both an art and a science to create these synthetic pathways. There's a bunch of reasons to do it. Sometimes there's industrial importance, and you actually have to make it for industry. Another is some of these are natural products, things that we find in nature in order to better study them and study their properties. Being able to synthesize and vary them is important. So lots of reasons to do synthesis. And do go ahead and read that article. I think it's a pretty good one. So this semester you won't be doing 140-step syntheses. We'll be looking at problems such as how we can prepare an alkyne from an alkene, how we can prepare an epoxide from an alkyl halide. You will have to combine several syntheses or several reactions that you've learned about in order to do these transformations. Complex mechanisms, the other thing that we're going to just start exploring and then do more of next semester, is that we get these like weird things happening and we need mechanisms in order to explain how they happen. And so you'll start to explain some of that, how things happen. And indeed, when you do your end of semester presentations, I'm going to ask you to really focus on something that, that you'll want to be able to explain by mechanism. So overall addition reactions. Okay, so here is what an addition reaction is. It's where you start with an alkene and you add an atom to one of the carbons of the alkene and an atom to the other atom of the alkene, and you wind up with sp3 hybridized carbons, single bonds, 2 new sigma bonds, in place of the pi bond. And so, for instance, this is a reaction called a hydrohalogenation. In a hydrohalogenation, you add a hydrogen and a halogen to the double bond. And so each of the carbons that was involved in the double bond will then in the product have a sigma bond to either the hydrogen or the bromine. You can also do addition to an alkyne. Essentially, these additions will occur twice. Whoops. And so you could add 2 equivalents of, for instance, hydrochloric acid, and now we've added 2 hydrogens and 2 chlorines to 2 pi bonds. All right, so let's see here. Can't quite get that over. Let's see. There we go. So, additions are super common in industry as well as the laboratory, like a research laboratory. And the common things that we see is we can do a hydrohalogenation, which I'll show you the mechanism for in a minute, a hydration, which we'll also look at. You can also do halogenations, as we see here, where we actually add two halogens to our double bond, one on either side of that double bond. And then with triple bonds, we can also do hydrations, or we can do hydrohalogenations. We can do halogenations, etc. One of the places that you might just want to connect the addition to is the addition, for instance, here of water in metabolism in the TCA cycle. And let's see here, you might be able to find another addition in there. It's kind of hiding though. It's actually over here. There's an elimination followed by an addition to give a rearrangement overall. The OH looks like it kind of jumps from one carbon to the next, but what's actually happening is elimination followed by addition. So you do see addition reactions. They're really important to synthesis and in our bodies, etc. All right, so like I've mentioned before, there's 3 different types of additions: hydrohalogenation, hydration, and halogenation. So let's just look at those first 2. Okay, so here is the mechanism of hydrohalogenation, and the hydration is going to be really similar. Same idea. So the nucleophile is the pi bond. Is that weird? That might be kind of weird. It's not negatively charged. It's not a lone pair. The pi bond is not held super tight to these carbons like an sp3 hybrid orbital would be. And so because it's a little, those p orbitals, those pi bonds are a little bit looser, they're better able, they're more polarizable. They can reach out and grab something that's positively charged and electrophile like the proton here. So that leaves a positive charge in the product, and then along comes our second nucleophile. The bromide in this case forms a new sigma bond with our carbocation intermediate. So carbocations, that should be a red flag that we are definitely going to be seeing some rearrangements. So regiochemistry, remember regiochemistry is where in the molecule the reaction happens or the bonds form. And bottom line, the more substituted halogen is going to form. Okay, so notice there is an alkene right here. If the bromine goes on the end, you get a less substituted primary halogen. If it goes in the middle, it's a secondary halogen. This one's more substituted, it's the one that forms. The reason it forms, we have to go back to the mechanism. That's how we explain stuff. The reason that it forms is because the most stable carbocation forms. And this is really the other fundamental idea of this chapter, is that the product that you see is a result of the most stable intermediate. So a more substituted carbocation is more stable, and so that's the one that's going to form, and that's the one that would lead to the more substituted product. And there's this kind of choice of the less and more substituted because the pi bond is a nucleophile, and so when it kind of reaches out and grabs the proton, the question is, does the proton go to the more substituted or less substituted position? And it's going to go to the less substituted position on the end, leaving the more substituted position to be the carbocation. So another way to think about that is there's 2 electrons in this pi bond, and what they do in the first step of the reaction is there's 2 pi electrons over here. The 2 pi electrons jump from that pi bond to the proton. Okay, so since they're leaving this carbon in the middle, that carbon becomes positively charged, and then you have a proton at the end. Or another proton at the end, I should say.